Hi, I'm Keon, and this video I'm going to show you 3 examples of how to use various methods to show if a series converges or diverges. So the first question is a sum from 1 to infinity of 1 over 2 to the n minus 1 over n plus 3. You might think this is um, telescoping series, but it actually not, because in telescoping series the two fractions which we have should be kind of similar, so we can find a connection and then evaluate that. But in this case this is not, and the only option we have is to break this sum into 2 parts and evaluate them individually. So what we will have, if you break them up, I'm going to use this color. We'll get the sum from 1 to infinity of 1 over 2 to the power of n, and then minus the sum from 1 to infinity of 1 over n plus 3. Okay, so now the first part, this is just a convergent geometric series because their common ratio is 1 over 2, which is less than 1. So for evaluating it, we just take the first term, 1 over 2, divided by the 1 minus the common ratio. If you evaluate that, we just get 1. And then we should subtract minus. The second part, 1 over n plus 3, reminds me of the harmonic series, 1 over n, but the difference is that this starts from 1 over 4, but the harmonic series starts from 1. It differs in the terms, but if you use the limit comparison test to the harmonic series, the limit will go to 1, and the limit exists and greater than 0, so we can say that this is divergent and goes to infinity. And then 1 minus infinity is just negative infinity, so the whole series actually diverges. The second example is actually a type of telescoping series, and for evaluating telescoping series, first we take the fractions 1 over n plus 2 and 1 over n plus 3. Now we can analyze and see that the fraction, the denominators differ by 1. N plus 2 differs by 1 from n plus 3. So we take one term from the first fraction. So when we put 1 in the first fraction, we just get 1 over 3. 1 over 1 plus 2, 1 over 3. And then we should subtract, because there's a subtraction sign, by the last term, which is this whole fraction of 1 over n plus 3. And actually, let me write it here so it has a space. We have 1 over 3, and then minus 1 over n plus 3. Now we have found a partial sum for this telescoping series, and our job is to take the limit as n goes to infinity, and the answer to the limit is actually the sum of the series, sum of the telescoping series. So we should take the limit as n goes to infinity of this nth partial sum. When we put infinity into 1 over n plus 3, it goes to 0, so the whole limit goes to 1 over 3. So we know that the sum of the telescoping series is just 1 over 3. Our last example is it's written in, and it's not written in summation notation. We have 1 over e plus 2 over e to the power of 4 plus 3 over e to the power of 9, and so on. So first of all, let's write it in summation notation. So this is the sum from n equals 1, because the first fraction is the numerator is 1, and it goes on forever. So 1 to infinity. And then we have n at the top, and at the bottom we have e to the power of, and if you look at the powers, for the first one is 1, second one is 4, 9, so it's just n squared. Okay, so we can't use any of the tests like test for divergence, limit comparison, or direct comparison, And but if we look at this as a function, we can actually integrate this function. The integral is actually valid, and we can actually integrate it. So let's look at the conditions for the use of integral tests. So if we want to use the integral test for a series, the function sequence, which in this case is n over e to the n squared, if we look at it as a function, the function should be decreasing, which is definitely decreasing because e to the n squared grows much faster than n. So we can say that this is decreasing for this interval. It is definitely positive because if you put any term, this is definitely positive. E to the any power is positive, and then the numerator is also positive. And then it's definitely also continuous because for a function to be discontinuous, have a discontinuity, the bottom, the new denominator should be equal to 0, but e to the n squared never equals 0. So we don't worry about that. So we can go ahead and integrate it. So if we use the integral, actually we can integrate. So we can take the integral from 1 to infinity, and then we have n, and then we have over e to the power of n squared. And then we can see that we can use a u substitution, u equal to n squared. And then let's actually use, let's use x for this because it seems unreasonable to use n. So I'm going to use x. It doesn't matter any variable if you want. X to the power of e to the x squared, and then dx. So we can use a u substitution. I'm going to let u to be equal to x squared, and then du is 2x dx. So now we can see that we have a cancellation if we actually divide both sides by 2x, so to solve for dx. And this cancellation would lead to, and also because it's integral, it has boundaries, limits of integration, we should actually change the limits of integration using the substitution we made. So when we put 1, when x is 1, u is also 1. When x is infinity, it's also infinity. So the boundary doesn't change. And we have, if we divide by 2x, x is cancelled, so we just have 1 over 2. And then we have times 1 over e to the power of u. And then we have du. So if we integrate 1 over e to the power of u, what do we get? We get because it's e to the power of negative u, so it's negative e to the power of negative u, I believe. And then we should evaluate it from 1 to infinity. As it goes to infinity, e to the negative infinity is just 0, so we have 0. And then because it's 1, we have negative e to the negative 1, so we have minus, and then minus 1 over e. So all in all, we have 1 over 2 times 1 over e, which is the same as 1 over 2e. And definitely this converges because the integral converges. And that's it for this video.